Hey everybody, this is Larry. This is me going with Q3 of the weekly contest 261, Stone Game 9. It is like Final Fantasy 9 or something. I don't know. There's so many sequels. Is it really? I don't know. Anyway, hit the like button, hit the subscribe button, join me on Discord. This one is really hard for me. As you can tell, I had 3 wrong answers. You can see my approaches during the contest next. But yeah, so join me on Discord if you want to chat about this problem or other contest problems. There are a lot of smart people there. Maybe they have a better solution. But yeah. So this one, just to go over my thought process. I mean, I used a pen and paper. I wrote down a lot of examples. But the short answer is that every move is forced. And every move is almost permutable. I don't know how to otherwise describe it, but okay. But there's 2 things you can do first, which is that the actual stone values doesn't matter. It's just the value mod 3, right? Because you just have to do it by 3. So then now, the approach that I asked myself is I tried a couple of ways to do this, but the core part of what I tried to do is, can Alice win? Right? I mean, obviously, maybe this isn't obvious, but like, maybe the better question is, in what ways can Alice win? Right? And in this case, the first move Alice can make is Alice cannot play 0. So what does that mean? So then Alice has to play 1 as the first move, maybe, right? And then now Bob has either 0 or 2 to play, and is forced 0 or 1 to play, and is forced because Bob cannot play 2. And as a result, in an awkward kind of way, this becomes. So I'm not gonna lie, this part I have trouble with during the contest, and I still have trouble with explaining, though, like, it was a very intuitive step or intuitive leap. Like I said, I don't have a strong proof, but the idea is just around a sort of parity and a number of moves left. Basically, you greedily. So the idea is that it actually doesn't matter whether Bob plays 0 or 1, because the number of moves left will always make it so that so the parity matters of who goes and who is forced to play the losing move. But the 0 and the 1 actually doesn't matter. Like, it doesn't matter what Bob plays, because everything is almost predetermined by the number of stones that are left. Okay. It's probably not convincing what I'm saying, but that, and maybe we'll learn together in a future part. Maybe come join me on Discord and you'll maybe see the follow-up. But that's basically the idea I have here, right? And then the question is, can Alice win here? And then the other move that Alice can do is Alice can play 2. And then Bob, of course, has forced to be 0 or 2. And of course, in this case, let me finish going through a little bit. If Bob plays 0, then Alice has to play 0 or 1 again. And therefore, in a weird way, and it's hard to visualize this, but the number of possible moves dwindled and then shifts from. It's kind of like the NIMS and parity, except for this is mod 3, right? So it's a little bit harder to visualize, but I don't know. It's a very weird problem in general. So yeah, so then my thing is, okay, if Alice plays 2, can she win? Right? So that's basically what I did with this one. I wrote, okay, go 1 or go 2, and go answering the question, can Alice win with first move of X? Yeah, and basically I go, okay, if you cannot play this move, we just ignore it because you cannot play this move. Otherwise, Alice plays this move, and then now it's Bob's turn. does Bob have a move that he can play, right? So we go through every possible move of 0, 1, and 2. We make sure that the total is mod 3 is not 0, or otherwise it'll be divisible by 3. And then we make sure, obviously, that there's a count. If we could find it, then you play it. Basically, just play any move that you can. If not, then we see whose turn played the last move, and then we turn true or false, depending on if it's Alice or Bob. And then at the very end, we return false, because if we played every stone, then it's false, right? Because there's just no more moves left for, and then Bob wins is what I mean. So this is why this is false. Yeah. As you can see, this is linear because we do a linear time thing here, and here this is also linear because that's the size of the input. So yeah. So linear time, linear. Is it linear space? No, actually it's constant space, because this one has at most 3. It uses 3 spaces, right? So yeah. So linear time, constant space, and that's all I have with this one. Yeah, I don't know that this is a great explanation, but hopefully, we'll jumpstart a conversation, and we'll all kind of think maybe there's a better way to think about it. Let me know what you think, and let me know how you did it if you solved this problem. And you could see. I actually did try to do a couple of logical things during the contest with if statements, but yeah, I just couldn't figure it out. And this intuition was something that I had very early on, but like I said, I couldn't prove it during the contest, and I don't really have a proof other than proof by AC. I don't really have a good proof now. So, but yeah, that's all I have for this one. I will see you later, and you can watch me solve it live next. Okay. Each stone has a value. You're given stones I as a value. Okay. Any stone from there, the person loses if the sum of all the values all removed stones is divisible by 3. Huh. I mean, this doesn't matter, but let's see. If there are no remaining stone, then Bob wins. Any stone from stones. The sum of the values all. So basically, okay. So the first stone we move is a 2. That's a lot though. I was gonna do something n cubed, but well, if I remove a 1, this is an awkward one. Anyone solve it yet? Nope. I think this is the first step. I don't know how to solve it. Okay. So if you remove a 0, you can remove a 0 to begin with. So, okay. What are the division trees? Alice come to? If Alice removes a... Okay, so that starts from the beginning. Alice removes a 1, then Bob can return a 0 and a 1, and then Alice can return Okay, let's just say it's 1, 0, and then the next one will have to be 1 or 0. So let's just try 0. The 0 can go all the way, and they kind of match, right? So then what happens, we do 1 and then 1, but then now you can do 2, so then now it goes back to 1. I don't know, these problems are always a little weird, but okay, so here they think Bob can always win. Bob can always win because if Alice chooses a 1, then Bob chooses a 0, and then then you have 2. Alice moves a 1, moves a 0. So, alright, this is actually what I was saying. Don't know that I know how to solve this one. Two, 2, 1. And n is too big. But is there anything we can do? What's a safe state? I guess that's the question. Safe state is if it's at 1 or 2. But this depends on the edges as well, doesn't it? Wait, can we look backwards? So we know that if everything is removed, this is a winning state for Bob. So then now we go up 1. What's a winning state for Alice? The winning state for Bob is this. Then if Alice has a winning state if what if this is 210, right? 210 is a losing state for Bob. What if it's 11? Well, 11 is losing. When can Alice win? Maybe that's a better question. Alice can win if... Maybe this is a dumb question. I don't know. I don't know another way where Alice can win. Alice can win if... Well, the zeros don't matter. So I think we can reduce this to n squared, but that's still too long. So what if it's 120? 110. Alice can win only if there's a path in which Bob has to choose a 3, right? So that means that if, so okay, 1, 2 is a winning state for one winning start. What is another example? Even 1, 2, 0 is no good. So is there another weird one? Like well, if there's 2 1s and 2 2s, then you pick a 1, Bob picks a 1, Alice choose a 2, and then Bob was forced to choose the last 2. I guess that's a winning state. If there's 3 1s and 3 2s, then you go 1 1, 2 2, 2 1, and then 2 1. Okay, oops. Okay, so 1 1, because you're forced to choose a 1. And then 2, so keep it. You can maybe do it 2 as well. No, you have to choose a 1. So then now what happens? And now Alice is choose to force a 2. And then Bob has to choose to force a 2, in which okay. Let's say there's 4 1s and 4 2s, but okay. Because in every other case, Bob can at least just play it out. I think that's the key observation, maybe. So 1 1, 2 1, and then now Alice can choose a. Well, Alice is forced to choose a 2, and then now okay. I think we have similar logic going the other way. Okay. So I think Alice only wins if count of 1 is equal to count of 2 and count of 0 mod 2 is 0, then return true. I don't know if this is true though. I don't know how to attack this one. True, false, false. Let's give it a submit and get a wrong answer maybe, and then see what the wrong answer is. Okay. Oh. This has to be greater than 0. Otherwise. Okay, this is an edge case, I suppose. Because. Yeah, okay. If count of 1 is equal to 0 and count of 2 is equal to 0, we return false, because that means that you choose 0 and then you lose immediately as Alice. So yeah, okay. Well, that's unfortunate, but I'm gonna get another wrong answer. Okay. I don't know how to do this one. This is one of those weird ones. Okay, let's look at this answer. Why is it wrong? So this the answer should be true, so Alice can win. So I was wrong on this then. Okay. What a disaster. A lot of people that only 5 or 6 people got it. So, and they got 2 wrong answers. So maybe my approach isn't that well. But I think maybe this is a good insight one. So let's dig into it a little bit. So you have 2 5s, 1 1, and 3 0s. 5 2s, not 2 5s. And this is good because. Okay, so Alice has to choose either 1 or 2. So let's just say Alice chooses a 1. Then the second. Oh. Yeah, I guess so. I guess the other case is because chooses a 1. Okay. If count of 1 is equal to 1 and. And okay, so then now here count 2 is greater than 0 and count of 0 mod 2 is wait, the 3 zeros, right? So that means that 1 2 2 2 and then 2. So then why can't, no, that's not the winning condition, is it? Okay, in this case, and then okay, I think I have this one backwards. No, that's not right either. So yeah, I think I know how to do it because everything is forced. So then okay. Right, I think that's the key trick, is noticing that everything's forced. I okay. Can Alice win if she picks up 1 to begin with? Right. The 0 is a little bit weird, but I think that's fine, maybe. So okay, so Alice chooses a 1 first. Then now Bob can either choose a 0 or a 1. Or just a lot of 2s. So the answer, okay, so let's say I think the 0 is making it confusing for me. Okay, so let's say Alice chooses a 2 on this one, and then and that means that Bob has to choose either 2 or 0. Let's just say he chooses 2. Then Alice chooses a 2 because he's forced to, or 0, but the 0 doesn't ring. Oh, but I just say 0 for now. And then Bob can choose a 0, and then Alice chooses a 2, and then Bob chooses a 1, and then now 2, and then Alice just loses, so there must be a better way. So chooses 2, 0, 0, and then now Alice chooses, Bob is forced to choose a 0, and now 0s are done, so then now Bob has 2, 1, yeah, so this is 5, but that means that, yeah, okay, so that means that Alice has to choose a 1, Bob has to choose 0, and then now no choice for Bob or Alice. And Alice chooses a 2, so loses, right? So that doesn't make sense. How does Alice win this one? I actually don't know how Alice wins this one. Can start with 0, so it starts with 1. So 1, but then that means that Bob has to choose a 0. And that means that Alice has to choose a 0, so Alice would have to at least eventually hit a 2. So okay, so that means Alice has to choose a 2. Bob has to choose a 0. Alice has to choose. Oh, I guess Alice can choose a 2. But then now Bob can choose a 1. Or just 0. And then now there's 4, so Alice is forced to choose a 1. Bob doesn't even care because now it's 5, so then it'll never. I don't get it. How does Alice win on this one? Did I miss something? Okay, so we start at. I think this is just Nim's game too. I think I'm just messing it up a little bit. Now, because the 2 doesn't cancel the 2 out on this one, right? So then that means that you have so it's not quite that. I don't know how to do this one, but apparently people know how to do cube 4 quicker. A lot of people know how to do this one now, so maybe I'm wrong, but I don't know how to do it. I don't even know how you get the right answer on this one. So There's 5 2s. So you remove a 1. I don't get how Alice's win. So 2. Forced to put a player 0, and then now Alice could choose a player 2. 1. 5. Oh, I was wrong about that one, Because 5 and a 9. Okay. I forgot that 9 is a multiple of 3. That's just awkward. Okay. So now what is 2 and then 1? Well, you can play 1, so it's 2. And then now you play 1. You can't play 1 either, so now you play 0. So then now play 0. And then now you play 2. This is 4. This is 5. And then now you have to play up to 9. Okay. I can see why Alice wins this one. I don't know how to prove that though. These are the 2 paths that Alice can take, and everything else is forced. Yeah, I don't know that this is quite right per se. I think the decision is interesting. I don't know how to force the decision, but maybe everything is forced. Let's see. Alright, Alice plays a 1, so let's just say 1. Yeah. So then now is that though? It's not really forcing that way. Because then now you have 2 and then 2, which is the one move that I haven't thought about. Now it goes to 4. which is 1, I guess. And then because of here, then you're forced to pick a Z, or you can pick a 1, I guess. There's 2, so then now you have to figure out 2 anyway. So that means that this is still 1. And then now you're picking a 0, 0, 0, and then 2. I don't know. There's a weird problem. I feel like I'm missing something obvious on this one. So, okay. This is state 2, this is state 2, this is state 1. I don't know if this is right, but we'll see. Yeah, okay. Okay, so then now, for example, we just do and then now Bob goes, right? Bob is forced to go okay. Then we break count of t minus 1. Right. Okay. So then if all else fails, so if not found, true. Okay, let's just see. If turn goes to 1, that means that is Bob's. No, if it's 0, I think it's minus 1, but because we take the first turn here. But if it's 0, that means that it was Bob's turn. So then we return true for Alice winning, otherwise we return false. Okay. Go 1 or go 2, maybe that's probably good enough. Oh, no. Why did I get rid of the things? Okay, but this is weird because why did I get rid of the things? I clicked on use example case by accident. Oh, I guess I have this one, and the other one is just 3 anyway, I believe. So okay. So expected true, that's good. 3 expected false, but why would I get 1 for this one? This one we want it to be false, but return true. Why? Tell me why. Okay, so if oh wait, okay, let's just print. Okay, so this is the one that I'm getting true on for some reason. Okay. So for x is equal to, did I mix it up? Yeah, I definitely mixed it up, because current should plus t mod 3. Well, that made it even more wrong, so that's a little unfortunate. Because before that, this was false. Well, that's fine. Oh, I also, because this doesn't really work, that's why. Okay, let's see. Okay, I need to redo this, that's why. Okay. Okay, I think this now matches what our expectation is. Let's YOLO a little bit again, because I don't know what else to put here. Anyway. Okay, that's unfortunate, actually. So there's just 7,000. Why did I print it twice? Oh, because I put it inside. Okay, 70,000 ones. I put true, but the answer is false because there's no 2. That's why. Silly mistake. X is equal to 0. We return. Silly mistake. You can't win because you can't use it. So okay. So that looks good again. Do I have any printing statement? No. Okay. Let's give it submit. I actually had this intuition earlier on, but I couldn't prove it. So, oh well. Yeah, hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem and other contest problems. Yeah. Stay cool, stay healthy, to good mental health. Have a great rest of the weekend, and I will see you later. Bye bye.